So today's session is again MT5504 mathematical programming based on BGAM method. We are in the third stage, means we have seen previously two problems based on BGAM method, and now we are starting the third problem. We have seen that whenever you are having one constraint with either of the form greater than or equals to or of equality, then we introduced one artificial variable to get the solution of as an initial solution, and then we tried as a simplex method to get the optimal solution. So today here we will start with two constraints which are having equality in the sign. So let's see one problem. First problem is you have to maximize z is equals to 3x1 plus 2x2 plus x3 subject to constraints 2x1 plus 5x2 plus x3 is equals to 12 and 3x1 plus 4x2 is equals to 11 with x1, x2 and x3 are greater than or equals to 0. If this is given situation, then to get initial basic feasible solution we are not having any need to get to first of all this is already in the standard form, so we cannot introduce another variable, and to get initial basic feasible solution you can start with taking x3 is equals to 0 and find out x1 and x2's value, so that is okay. But now if our situation is like this, that x2 and x3 are non-negative but x1 is unrestricted in sign, then so first of all, to get a standard form of this, we have to do is write x1 as difference of two variables x1 dash and x1 double dash. Write x1 as this, so you can reach to the standard form. So first of all, the standard form of given linear programming problem is, instead of x1 we have to write x1 dash minus x1 double dash. So maximize z is equals to 3 times x1 dash minus x1 double dash plus 2x2 plus x3 subject to constraints 2 x1 dash minus x1 double dash plus 5x2 plus x3 is equals to 12, that is from the first constraint, and from the second constraint you are having 3 x1 dash minus x1 double dash plus 4x2 is equals to 12. Now here you are having x1 dash, x1 double dash, x2, x3 all are non-negative. Now if you want to get an initial basic feasible solution, right now from this situation you are not able to get directly initial basic feasible solution. If you take your x1 dash, x1 double dash, x2 and x3 is 0, if we can take this, then this equality signs are not satisfied, means this is not in a required position to get our solution, means initial basic feasible solution. So as we have done previously, we will introduce two artificial variables. But see, here x3 itself is working as an artificial variable. see here this constraint contains x1 dash, x1 double dash and x2. So x3's value is not depending on the second constraint. So you can take x3's value as 12. You can start in two ways. See, I am writing both the ways. Okay. So first way, as the usual way, means introduce artificial variable in the both the cases. That is, your problem will be converted like maximize. This is case 1. Okay. You can start by case 1 like this, that maximize z is equals to 3 x1 dash minus x1 double dash plus 2x2 plus x3 subject to constraint 2 x1 dash minus x1 double dash plus 5x2 plus x3 plus a1 is equals to 12. 3 x1 x1 dash minus x1 double dash plus 4x2 is plus a2 is equals to 12. So and of course, as x1 dash, x1 double dash, x2, x3, a1 and a2 all are non-negative. In this case, you can take that your x1 dash, x1 double dash, x2 and x3 is 0, and you will have a1's value 12 and a2's value again 12. Sorry, in problem I have taken 12 both the cases. Here it is 11. Okay, so everywhere it should be 11 instead of 12. And here also it is 11. So x2's value is a2's value is 11. Okay. Now that is the usual way to solve this problem, and now you can start as a simplex problem. Let's see in a different way, that is case 2. So here there is no need to introduce artificial variable, so we will not introduce there. Here of course coefficient of a1 and coefficient of a2 are minus m in both the constraints. So you have to start with this. Okay, in the first constraint there is no need to introduce artificial variable because x3 itself is directly giving you answer. So instead of going towards that introducing artificial variable in the first constraint, we will just introduce in a second constraint. Means our problem will be look like this: 3 x1 dash minus 3 x1 double dash plus 2x2 plus x3. I am writing the coefficient of artificial variable at the end. Okay, subject to constraints 2 x1 dash minus 2 x1 double dash plus 5x2 plus x3 is equals to 12. 3 x1 double dash minus 3 x1 double dash plus 4x2 plus a is equals to 11. So I have introduced only one artificial variable, and x1 dash, x1 double dash, x2, x3 and a are non-negative. Okay, so here we have to write minus m times a. Here again m is too much large number. Okay, so you can start from the first case also or from the second case also. In the both cases you will end up at the same solution. So I am not going toward this the first case because it is having more variables, so calculation for the first case is larger. I am directly starting with the second case. You can try at your home that from the first case also we are getting the same solution. Okay, so here To get the initial basic feasible solution, I am considering x1 dash, x1 double dash, x2 are 0. So if that is the case, then x3 will be 12 and a will be 11. So in the basis you are having x3 and a. So writing the first initial table from that, so in basis you are having x3 and a. x3's value is 12, a's value is 11, that is xb, x1 dash coefficients, x1 double dash coefficients, x2's coefficients, x3's coefficients and a's coefficient. x1 dash coefficient in your objective function is 3, x1 double dash coefficient is -3, x2's coefficient is 2, x3's coefficient is 1, artificial variables is -m. So now writing the coefficients here, that is CB, x3's coefficient is 1, a's coefficient is -m. Now writing a constraints coefficients. So for the constraints coefficient, x1's coefficient in the first constraint is 2, x1 double dash coefficient in first constraint is -2, x2 coefficient in first constraint is 5, x3's coefficient in first constraint is 1, and artificial variable is not appearing in the first constraint. Then from the second constraint, we are having x1 dash coefficient is 3, x1 double dash coefficient is -3, x2's coefficient is 4, x3 is not there, and a's coefficient is 1. So now you have to evaluate zj. Zj is evaluated in a way that 1 is multiplied with 2 plus -m is multiplied with 3. So 1 is multiplied with 2 is 2 plus -m is multiplied with 3, so -3m. And then doing the similar for x1 double dash. So -1 times 2 is -2, -m minus 3, so plus 3m. 1 times 5 is 5, plus 4 times -m, so -4m. 1 times 1 is 1, and here it is 0, so here it is 0 times 1 is 0, and -m times 1, that is -m. Now Cj minus Zj, so 3 minus 2 minus 3m, so 3 minus 2 is 1, minus 3 is plus 3m. Now here -3 minus 2, so plus 2, so -1 minus 3m. Then here 2 minus 5, so -3 minus -4m, so plus 4m. 1 minus 1 is 0, and m minus m is -m is 0. Okay, so maximum from the Cj minus Zj is for this. See, m is too much large, so 3 times m is again too much large, but in comparison to the 4m, 3m is smaller, so 4m is again more than everything. So here you are getting the maximum value. Okay, so x2 will enter a basis. Now to evaluate which variable will leave a basis, you have to find out the replacement ratio. So for the replacement ratio, you have to divide 12 by 5 and 11 by 4. So find out which one is smaller. So 12 by 5 is smaller than 11 by 4. If you are not able to see directly, then you can calculate, means multiply both by 4. So here 12 times 4 is 48 by 20, and here multiply with 5, so it is 55 by 20. So this is a smaller quantity, so corresponding variable will leave a basis, so x3 will leave a basis and x2 will enter a basis. So we have to make this quantity 1 and this quantity 0 by applying RRE process. So that can be obtained by, first of all we have to make a table, so let's write that xb, b, cb, x1 dash, x1 double dash, x2, x3 and a. Coefficients are 3, minus 3, 2, 1 and minus m. See, here we are calculating for a because a is not removed from basis. Okay, so here x3 is replaced by x2, a is there itself, so here coefficient is minus m and x2's coefficient is 2. Now to make this entry 1 we have to divide by 5, so here it will be 12 by 5, here it will be 2 by 5, here it is minus 2 by 5, here it is 1, here it is 1 by 5 and here it is 0. Okay, now to make this entry 0, we have to do is multiply this row by 4 and subtract from here. So 12 by 5 times 4 is subtracted from 11, so your quantity is 7 by 5. Then here 3 minus 4 times 2 by 5, so it is 7 by 5. Here it is minus 7 by 5. Here it is 0, then it is minus 4 by 5, then 1. Okay. Now we have to calculate ZJs. So to calculate ZJs, again we have to do is multiply 2 with 2 by 5 and minus m with 7 by 5 and add up them. So 2 times 2 by 5 is 4 by 5 plus minus m times 7 by 5, so minus 7 by 5 m. Then 2 by times minus 2 is minus 4 by 5. Then minus m minus 7 by 5 plus, so plus 7 by 5 m. Then here it is 2 times 1 is 2, 2 times 1 by 5, 2 by 5, and minus m times minus 4 by 5, so plus 4 by 5 m. And here 2 times 0 is 0 and minus m times 1 is m. Okay. Now you have to evaluate Cj minus Zj. So Cj minus Zj is 3 minus this quantity is so 3 minus 4 by 5 plus 7 by 5 m. Here it is minus 3 plus 4 by 5 minus 7 by 5 m. Here it is 2 minus 2 is 0. Here it is 1 minus 2 by 5 minus 4 by 5 m. And here it is m minus minus m, it is 0. Sorry, here it value is minus m and then minus m minus minus m is 0. Okay. So we are having Cj minus Zj, so evaluate for which value you are having maximum value. So 7 by 5 m is too much large number because m is too much large. Okay, this quantity and this quantity are negative with m, so you are having smaller in the quantity. So this is a larger quantity, so x1 dash will enter a basis. Okay, now which variable will remove the basis? For that you have to find out the replacement ratio. So for the replacement ratio you have to divide 12 by 5 by 2 by 5, so 12 by 2, and 7 by 5 by 7 by 5, so 1. So 12 by 2 is 6 and 1 is 1, so 1 is smaller than 6. So your A will remove a basis. So now onwards we will not calculate anything for A. So again we have to make a table that CB, B, XB, X1 dash, X1 double dash, X2, X3. Here in basis you are having X2 and X1 dash. Coefficient for X2 is 2 and X1 dash coefficient is 3. B's values. Now we have which entry will be 1. So this here you are entering and here you are leaving basis. So this quantity will be 1 and this quantity must be 0 by applying array process. So all you have to do is divide this by 7 by 5. So first of all we will write corresponding values. So divide this by 7 by 5. So here you are having value 1. Here you are having value 1, here you are having value minus 1, 0, minus 4 by 5 by 7 by 5, so minus 4 by 7. Then to make this entry 0, we have to multiply this row by 2 by 5 and subtract from here. So you have values 2, 0, 0, 1, 3 by 7. Okay, now again sorry, let me write CJs. So CJs are 3, minus 3, 2, 1. Okay, we are not calculating for artificial variable now. Now we evaluate ZJs. ZJs are evaluated in the way that 2 times 0 plus 3 times 1 is 3. 2 times 0 plus 3 times minus 1 is minus 3. 2 times 1 and 3 times 0 is 2. And 2 times 3 by 7. 3 times so 6 by 7 minus 3 times 4 by 7. So 12 by 7. That is ZJ. And CJ minus ZJ are 3 minus 3 it is 0, minus 3 minus minus 3 is 0, 2 minus 2 is 0, and 6 by 7 minus 12 by 7 is minus 6 by 7. Sorry, 1 minus this quantity. So first of all this is minus 6 by 7. And 1 minus minus 6 by 7. So 1 plus 6 by 7. Whatever it is greater than 0. So the corresponding variable must be entered in a basis. So again we have to find out the replacement ratio. To find out the replacement ratio we have to divide 2 by 3 by 7. So that is 14 by 3. And here quantity is negative, so ratio is infinite for that. So corresponding x2 will leave a basis and x3 will enter a basis, and we have to make this entry 1 and this entry 0. Okay, so for doing that again we have to make a table. So for making a table, let me write CB, B, XB, X1 dash, X1 double dash, X2 and X3. X1 dash coefficient is 3, minus 3, 2, 1. In basis now X2 is replaced by X3. So we are having X3 and X1 dash. X3's coefficient is 1 and X1 dash coefficient is 3. Now apply RRA process. So first of all, to make this, we have to divide by 3 by 7. So quantities will be 2 by 3 by 7 is 14 by 3. Here 0 by anything is 0, 0 by anything is 0. 1 by 3 by 7 is 7 by 3, and 3 by 7 by 3 by 7 is 1. Now to make these entries 0, we have to multiply this row by 4 by 7 and add it in the this row. So by doing that, we are having values here 8 by 3, here it is 1, here it is minus 1, here it is 4 by 3, and here it is 0. Now again we are in the table. Again we have to evaluate value of Zj. So Zj is 1 times 0 is 0, 3 times 1 is 3, 1 times 0 is 0, 3 times minus 1 is minus 3, 1 times 7 by 3, so 7 by 3, 3 times 4 by 3 is 4, and 1 times 1 is 1, 3 times 0 is 0. Okay, so Zj is this, Cj minus Zj. So 3 minus 3 is 0, minus 3 minus minus 3 is 0, 2 minus 7 by 3 plus 4, so it is minus 2 minus 7 by 3, whatever its calculation is. Okay, and here it is 1 minus 1 is 0. So we are having solution that all Cj minus Zj's are less than or equals to 0. So this solution is an optimal solution. Okay, so we are having optimal solution at x1 dash is equals to 8 by 3 and x3 is equals to 14 by 3. So of course these are there, so other variables are 0. So x2 is 0 and x1 double dash is 0. So for that you are getting the optimal solution. So what is your x1? x1 is x1 dash minus x1 double dash. So x1 dash is 8 by 3 and x1 double dash is 0. So your x1 dash, x1's value is 8 by 3. So your optimal solution is reached at x1 is equals to 8 by 3, x2 is 0 and x3 is 14 by 3. And corresponding value of z, so maximum value of z is again from the original problem 3x1 plus 2x2 plus x3. So 3x1 plus 2x2 plus x3, that is 3 times 8 by 3 plus 2 times 0 plus 14 by 3, that is 8 plus 14 by 3, whatever value is, that is your optimal solution. That is 38 by 3. Okay. Now after looking at the original problem, you are having a situation that, see, here x3 is in a basis, x1 dash in a basis. So here your x1 dash is in basis, x1 x3 is also in basis. So here value is 0 and here's value is 0, but you are getting extra value 0 here also. So here you can insert x1 double dash in a basis, but in that case also you will get the same solution. Means as a solution you will reach at your x1's value is 8 by 3 and x3's value is 14 by 3. Okay, so this is solution to the given linear programming problem. So this is your optimal solution to the given linear programming problem. So today we have seen that whenever you are having a linear programming problem with more than one equality constraint, you can directly insert artificial variables in both the constraints and start solving that. Like the first case, here we have introduced artificial variable in both the constraints. Or smartly you can identify one variable which is not in the other constraint, or in another way find out any another basic feasible solution to the given linear programming problem to reduce the steps in the simplex process. See, here we have solved our linear programming problem by writing this as a first table, this is as a second table, this is as a third table, and in the fourth table. Okay, but if you can solve, you will try to solve a problem by considering the case 1, you will have one more table, that is in the terms of removing the artificial variable first a1 by some another variable. Okay, so in this way you can reduce steps in a calculation if you can identify some initial basic feasible solutions directly. So this is all today. We can I can give you one more problem based on the similar process, and I hope you will try at your home. So let's write down the problem that maximize z is equals to x1 minus x2 plus 2x3 plus 4x4 subject to constraints 2x1 plus 2x3 plus x4 is equals to 14. x1 plus x2 minus x3 is greater than or equals to 5. x1 plus x2 plus 3x3 plus x4 is less than or equals to 30 with all xi's are non-negative. So I hope you will find out the solution to the given linear programming problem, and till that means after doing that, stay at home and stay safe. Thank you.